Ladies and gentlemen, thank you so much for your attendance today. My name is Adil Abdurrahman, Electronics and Communications Engineering Department. I am a member in Microwave and RF Lab, Egypt, Japan University of Science and Technology, Egypt. I am happy to present our group work today. Most of this work has been published in well-known and impacted journals. The title of my first presentation is Coupled Defected Ground Structures, Resonators, Principles and Applications for Wireless Power Transfer. Today I'm going to talk to you about why do we need wireless power transfers, and we'll start with conventional wireless power transfer implementation techniques and applications. The different standards and products will be presented. We will talk about the defected ground structure resonators, which is the heart of the system. Then novel defected ground structure wireless power transfer structures will be presented. A dual band wireless power transfer using defected ground structures will also be introduced. Then the conclusion. We dream to convert from the complicated powering systems to free wireless power transfer systems. One can imagine how our life will be hassle-free to power electrical devices, electronic consuming devices, and many other applications like wireless pulse sensors or biomedical implants without interconnecting wires. Many organizations have adopted the idea of generalization of wireless power transfer in many applications. There are two main implementation techniques for wireless power transfer. The first one is the near-field coupling, which is called non-radiative technique. The second one is the far-field or radiative technique. The near-field coupling methods are the most popular for applications such as RFIDs, wireless charging of portable electronic devices, biomedical implants, or wireless pulse sensors. It can be capacitive coupling where power is transferred through the electric field. It can be inductive coupling where power is transferred between transmitter and receiver through the two coils close to each other. The resonant inductive coupling is used for mid-range application. At high frequency, the resonant type becomes a good choice to enhance the efficiency of power transfer. Far-field implementation techniques. Electromagnetic radiation makes energy transfer possible to realize larger transmission distances. Electromagnetic waves most commonly used in wireless power transfer are microwaves and visible light. This slide shows some of the applications of wireless power transfer that are found nowadays in our daily life or going to be found in the near future. These applications are portable electronic devices, electrical vehicles, biomedical implants, wireless pulse sensors, RFIDs. Standards and products. There are two different types of standards. The first is called QI standard and the second one is called KI standard, for cordless kitchen standard. We hope that standards can be created to enable safe and more convenient applications. The QI standard has been developed by the Wireless Power Consortium for inductive coupling of power over distances of up to 4 cm. Some of the manufacturers that are working with the standard like HTC, LG, Nokia, Samsung, and others. The parameters of one of these standards is frequency range from 100 to 200 kHz, wireless distance around 5 mm, charging voltage 5 voltage, charging current 0.5 to 1 amps. This slide presents the different types of coupling techniques, including inductive coupling, resonant inductive coupling, capacitive coupling, magnetodynamic coupling, microwaves and light waves. The title of the first part of this presentation is A Novel Technique for Compact Size Wireless Power Transfer Applications Using Defected Ground Structures. Let me introduce some information about defected ground structure resonators. A slot in the ground plane underneath the 50 ohm line behaves as a parallel resonance. The values of L, C, and R parameters of the equivalent circuit are calculated from the resonant and cutoff frequencies. Defected ground structure slot can take any resonant shape. To improve the quality factor of the resonator, a lumped capacitor can be added. To improve the quality factor of the defected ground structure resonator, a capacitor is added at the position of the maximum electric field. The distribution of the electric field within the defected ground structure slot depends on the operating frequency. The lumped capacitor has its maximum effect at the position of the maximum electric field. As shifting the capacitor from the center of the slot, its effect is reduced. As I mentioned, a lumped capacitor can be integrated with the defected ground structure slot to reduce the size by around 70% and improve the quality factor. By adding a lumped capacitor of 0.7 picofarad, for example, the operating frequency and size are reduced by 70%. The capacitor not only reduces the size but also improves the quality factor of the resonator. The unloaded quality factor has been improved from 10.9 to 98. This is due to the reduction of the slot length and hence the radiation loss. Defected ground structures are introduced to improve the performance of different types of filters, low pass and band pass filters. For example, it has been introduced to improve the performance of the stepped impedance low pass filter by realizing high inductance values using defected ground structures. Defected ground structures have been utilized to improve the performance and realize ultra-wideband band pass filters. More than this, defected ground structures are used by our group to implement a Stubless low-pass filter with improved performance. Coupled resonator, defected ground structure band pass filters. Where a coupled resonator filter has been realized using defected ground structure resonators as a building block. A three-dimensional second-order defected ground structure with a bandwidth of 1.12 GHz, a return loss of 19 dB, and a center frequency F0 of 4.9 GHz has been realized using defected ground structures, coupled resonators. Defected ground structure resonators are used to realize fourth-order cross-coupled defected ground structure resonator filter. A fourth-order cross-coupled resonator filter with two transmission zeros result from the cross-coupling between the first and the fourth resonator has been designed and fabricated and characterized. Another compact capacitor-loaded defected ground structure coupled resonators are used to design compact band pass filter. The title of the second part of the presentation is Design of Defected Ground Structure wireless power transfer systems using iterative optimization techniques. I will present on behalf of Dr. Sharif Hakan. Implementation of wireless power transfer using defected ground structures. Bulky coils are used in traditional techniques. These bulky coils are not suitable for implanted medical device and wireless powered sensors. New wireless power transfer techniques using defected ground structure resonator are more compact for implanted and buried devices. An H-shape defected ground structure coupled resonators are used to implement wireless power transfer. The system operates at 1.4 GHz. The elements of each resonator and coupling coefficients are extracted from the electromagnetic simulator. The equivalent circuit parameters L, C, and R of the resonator are obtained from the resonance and the cutoff frequencies. The coupling coefficient K is also extracted from the electric and magnetic frequencies. As an implemented example, maximum efficiency of 90% has been obtained at separation distance of 3.5 mm. Good agreement between the extracted circuit model and the full wave electromagnetic simulation has been achieved. The misalignment shift of the receiver in X and Y directions with respect to the transmitter has been investigated. Perfect face-to-face orientation leads to the highest efficiency. The shift in the X direction strongly affects the efficiency than the shift in the Y direction. The width of the slot can be optimized to provide more coupling and hence more efficiency. The distribution and the orientation of the electric field distribution is shown in this slide. This slide shows the fabricated structure and measurement setup. A vector network analyzer is used to characterize the fabricated device. This slide shows a comparison between the measured and simulated S parameters of the proposed wireless power transfer system using H-shaped defected ground structure resonators. Good agreement between simulation and measurement results. To improve the efficiency, an intermediate resonator with high quality factor are used to increase the total transferred power efficiency. A separation distance of 9 mm has been achieved with high efficiency. The presence of an intermediate resonator improves the coupling. A separation distance of 9 mm has been achieved with high efficiency. This slide shows the surface current distribution and orientation in each slot. The surface current distribution in the ground plane of each slot resonator makes it look like two parallel loop inductor. In this case, we can use quasi-static modeling. The equivalent circuit inductance, capacitance, and resistance can be obtained from the quasi-static modeling equations 1, 2, and 3 respectively. The value of the series coupling capacitor to the source can be obtained using equation 4. The surface current distribution in the ground plane of each slot resonator makes it look like two parallel loop inductors, which leads to the following disadvantages. Very short distance for maximum power transfer efficiency, 3.5 mm for 85%. Extra structures to get strong coupling and larger distance for transmission. The misalignment study between transmitter and the receiver in X direction has recorded a great decrease in transferred power at shift equals half of the slot length. The orientation's effect of the receiver at different angles with respect to the transmitter has been investigated. Perfect face-to-face orientation leads to the highest efficiency as a receiver rotates around Z-axis. Efficiency decays due to polarization misalignment. In this part, we will talk about the design of wireless power transfer systems using asymmetric structures. In this slide, a semi-H-shape DGS resonator is presented. Considering the current distribution loops, the semi-H-shape resonator consists of only one current loop, which relies nearly double of the inductance of H-shape that consequently increases the wireless power transfer efficiency and increase the transmission distance. The proposed structure for wireless power transfer is composed of two coupled semi-H-shape DGS resonators set back to back as shown in the slide. The equivalent circuit of the proposed structure is shown in the slide. The mutual inductance and the coupling coefficient are calculated from the shown formulas. A comparison between H-shape and semi-H-shape defected ground structure resonators is presented in this slide. A comparison between the optimum design parameters of the wireless power transfer system using H-shape defected ground structure and semi-H-shape defected ground structure resonators at 300 MHz. The H-shape defected ground structure is composed of two parallel loops. The opposite flow of the current in the H-shape leads to a poor coupling performance. Consequently, the efficiency of the semi-H-shape of the same size of H-shape is better. A measurement setup of the fabricated wireless power transfer systems using H-shape defected ground structure resonators and semi-H-shape defected ground structure resonators are shown in this slide. The H-shape defected ground structure wireless power transfer system achieves maximum measured efficiency of 68% at a transmission distance of H equals 13 mm. The semi-H-shape defected ground structure achieves a wireless power transfer efficiency of 73% at a transmission distance of H equals 25 mm. Comparison between H-shape and semi-H-shape defected ground structure resonators, orientation, angles, and misalignment. The left figure in this slide presents the misalignment performance comparison between the H-shape and semi-H-shape defected ground structure resonators, wireless power transfer systems. The semi-H-shape resonator shows no degradation due to the horizontal misalignment. In addition, the semi-H-shape resonator is not sensitive to the orientation as shown in the right figure. H-shape and its modified version, the semi-H-shape and the spiral strips defected ground structure, are shown in this slide. The self-inductance of the H-shape defected ground structure is low, which leads to the lower efficiency at larger distance due to the two parallel current passes. Only one current path is found in the semi-H and the spiral strips resonator. The spiral strips defected ground structure resonator provides the highest Q factor among the others due to the increased self-inductances. External capacitors are used to improve the quality factor for high efficiency. CPI is used to adjust the resonance and optimize the area. CLSI and CSTI are used for impedance matching. The different parameters can be optimized to get the desired specifications according to the constraint. The equivalent circuit elements can be extracted from the analogy of S parameters or quasi-static modeling. These parameters are used to optimize the required design. The right figure shows a glance of the simulated magnetic field for the symmetric 50 by 50 mm square at different phases. The left figure shows a glance of the simulated magnetic field for the asymmetric transmitter of 50 by 50 mm square and receiver of 30 by 30 mm square at different phases. The measurement setup for the fabricated wireless power transfer systems, symmetric and asymmetric, are shown in this slide. The simulated and measured S parameters for the proposed wireless power transfer systems are shown in this slide. As shown, the symmetric and asymmetric wireless power transfer systems operate at 49.5 MHz, and the measured results are in good agreement with the simulated results. This table introduces a comparison between our published work with others published work regarding measured efficiency, transmitter-receiver areas, and the maximum transmission distance. This comparison verifies that the proposed wireless power transfer systems using spiral strip DGS resonators can offer higher efficiencies than other published symmetric structures. The proposed spiral strips defected ground structure resonators provide a new, efficient, and compact design for asymmetric wireless power transfer systems. The offered symmetric wireless power transfer system, transmitter, and receiver have areas of 50 by 50 millimeter square, achieves a maximum efficiency of 84% at transmission distance H equals 50 millimeter. The offered asymmetric wireless power transfer system achieves efficiency of 78% at a distance of 40 millimeter. Transmitter and receiver areas are 50 by 50 millimeter squares and 30 by 30 millimeter squares respectively. The growing demand for resonant wireless power transfer technology, especially for near-field techniques, is driven by wide prospective applications such as portable consumer electronic devices and biomedical implants. Recent work in integrated wireless power transfer systems such as for implantable biomedical device aimed to transfer power and data wirelessly at separate frequencies. A new compact dual-band wireless power transfer system using interlaced defected ground structure resonators is shown in this slide. The proposed structure is characterized using Agilent Vector Network Analyzer. The measurement results show that the dual-band wireless power transfer system with insertion loss of -1 and -1.3 at 300 and 675 MHz respectively. The calculated wireless power transfer efficiencies are 80 and 73% at frequency F1 and F2 respectively. References related to the presented materials are shown in this slide. Conclusions. A defected ground structure provides higher inductance values than a high impedance straight line section. High quality factor defected ground structure resonators are obtained using the integration of lumped capacitors at the position of the maximum electric field. Capacitive loaded defected ground structure resonators are used to improve filter performance, a novel technique for high efficiency and compact size wireless power transfer systems employing quasi-lumped defected ground structure resonators is proposed. A wireless power transfer efficiency of 87% at an effective distance of 13 mm has been achieved using coupled H-shape defecting ground structures, while a wireless power transfer efficiency of 73% at an effective distance of 25 mm has been accomplished using coupled semi-H-shape defected ground structures. An analytic design method for the proposed wireless power transfer systems has been presented. The design theory has been verified through good agreement between electromagnetic simulations, circuit simulations, and measurement. More detailed information can be obtained from our published book. The title of our book is Compact Size Wireless Power Transfer Using Defected Ground Structures. The book contains 5 chapters as follows. Chapter 1, Introduction. Chapter 2, Basics of Wireless Power Transfer. Chapter 3, Wireless Power Transfer Using Defected Ground Structures. Chapter 4, Design Methods. Chapter 5, Future Directions. Thank you for your attention and waiting for your questions.